Okay, so let's continue. Okay, so the system can be solved as x sub 1 dot okay to x and n in terms of t dot to tk, provided that certain partial derivatives are continuous, provide that the n cross n Jacobian determinant. So I'm not really sure on how to read this sign, the mathematical symbol. Okay, so f sub 1 dot to f sub n. Okay, so over, I still don't know how to read this one. Okay, so x sub 1 dot to x sub n is not 0. Okay, for brevity, we shall adapt the following notation in this theorem. Points in n plus k minus the dimensional space r to the power of n plus k will be written in the form of x t, where x is equals to x sub 1 dot to x sub n. Okay, it belongs to r to the power of n, and t is equals to t dot t k is belongs to r to the power of k. Okay, so next. Next slide, Max. Okay, so let's proceed to theorem 13.7, the implicit function theorem. Okay, let f is equals to f sub 1 dot fn be a vector valued function defined to an open set S in R sub n plus k with values in R to the power of n. Suppose f is belongs to c to the power of 1 on S. Let x sub 0 and t sub 0 be a point in S for which f of x sub 0 and t sub 0 is equals to 0, and for which the n cross n determinant that djfi of x 0 and t 0 isn't equals to 0. Then there exists a k-dimensional open set t sub T0 containing T0 and 1 and only one vector valued function g defined on T sub 0 and having values in R to the power of n such that, okay, A, B, and C. Okay, A, G is belongs to C to the power of 1 on T sub 0, and B, G to T sub O is equals to X sub 0. It's not, oh, it's 0. Okay, f of g of t and t is equals to 0 for every t in t sub 0. Okay, let's prove. We shall apply the inverse function theorem to a certain vector valued function. F is equals to f sub 1 dot fn, and fn f sub n plus 1 f sub n plus k defined on S and having values in R to the power of n plus k. The function f is defined as follows. For 1 less than or equal to m less than or equal to n, let f sub m of x and t is equals to f sub m of x and t. And for 1 less than or equal to m and less than or equal to t, let f sub n plus m of x and t is equals to t sub m. We can then write f is equals to f and I, where f is equals to f sub 1 f and where I is the identity function defined by I of t is equals to t for each t and r to the power of k. The Jacobian g sub f x t then has the same values as the n cross n determinant that djfi of x and t, because the terms which appear in the last key rows and also in the last key columns of g sub f of x and t Form a k cross key determinant which ones along the main diagonal and zeros elsewhere. The intersection of the first n rows and n columns consists of the determinant that d, g, f, I, x, and t, and so this one, d sub I f sub n plus j of x and t is equals to 0, and for 1 less than or equal to I less than or equal to n, and 1 less than or equal to j less than or equal to k. Okay, so please next. Next, please next. A local inverse function g defined on y and having values of x such that g f of x and t is equals to the quantity of x to t, and such that g belongs to to the power of 1 or c of 1 on y. Now g can be reduced to components as follows. Okay, g is equals to v w, where v is equals to v sub 1 that vn is a vector valued function defined on y with values r to the power of n, and w is equals to w sub 1 w sub k is also defined on y but has values on r to the power of k, which we cannot determine v and w explicitly. Okay, the equation g f of x and t is equals to x and t were written in terms of components v and w, which gives us the two equation. Okay, so these are the equation, the v and the w. Okay, so just see it. Just read it. Okay, but now every point x and t in y can be written uniquely in the form of x on t is equals to f of x to the power of 1 and t to the power of 1. For some x to the power of 1 and t to the power of 1 in x, because f is 1 to 1 and x, and the inverse image of f to the power of negative 1 of y contains x. Furthermore, by the manner in which f was defined, when we write x and t is equals to f of x to the power of 1 and t to the power of 1, we must have t to the power of 1 is equals to t. Therefore, so this is the v and this is the w. Okay, just read it because I am not really sure on how to read those ones, so just read it. Okay, hence the function g can be described as follows. Given a point x and t in y, we have g of x and t is equals to x to the power of 1 and t, where x to the power of 1 is that point in R sub n, such that x and t is equals to f of x to the power of 1 and t. Okay, this statement implies that, so this one, f v of x and t is equals to x of t for every x and t and y. Okay, so now we are ready to define the set of t sub 0 and the function of g. Is it 0 or o? T sub o. And function g in the theorem, let t sub 0 or o is equals to t, and t is belongs to r to the power of k, and 0 and t is belongs to y. Okay, please next. Hence, the Jacobian g sub f of x sub 0 and t sub 0 is not equals to 0. Also, f of x sub 0 and t sub 0 is equals to 0 and t sub o. Therefore, by theorem 13.6, there exist open sets x and y containing ay bakit tuloy? Okay, so containing x0, x sub 0 and t sub 0 and 0 and t and o respectively, such that if is 1 to 1 on x, and x is equals to f to the power of negative 1, and y also there exist. Okay, next. And for each t and t sub o, define g of t is equals to v o and t. The set of t sub o is open in R to the power of k. Moreover, g is belongs to c of R to the power of 1 on t sub o, because g belongs to c um to the power of 1 on y, and the components of g are taken from the components of g. Also, g of t sub o is equals to v o 0, and t sub o is equals to x sub 0, because 0 and t sub 0 is equals to f x sub 0 and t sub 0. Finally, the equation f v of x and t is equals to x and t, which holds for every x, t, and y's, yields by considering the components of r to the power of n. The equation f of v of x and t is equals to x. Taking x is equals to 0, we see that for every t and t sub 0, we have f g to t is equals to 0. I am not really sure on how to read this one, because I am not really sure on how to read mathematical symbol. And this completes the proof of statements A, B, and C. Okay. So it remains to prove that there is only such one such a function g, but this follows at once from one-to-one character of f. If there were another function, say h, which satisfied the c, then we would have f g of t, and t is equals to f h of t and t, and this would imply g t of t is equals to h of t, and t or g of t is equals to h of t for every t and t sub 0. Okay, please next. Extrema of real valued functions of one variable. Okay, so we are here now on the 13.5. In the remainder of this chapter, we shall consider real valued functions f with a view toward determining those points, if any, at which f has a local extremum, that is, either a local maximum or a local minimum. Okay, please next. We have already obtained one result in the connection for functions of one variable. So, okay, in the theorem 5.9. In the theorem, we found that a necessary condition for a function f to have a local extremum at an interior point of c of an interval that is f I really don't sure. I am not really sure on how to read this. Provided that f to the power of 1 of c exists. This condition, however, is not sufficient, as we can see by taking f of x is equals to x squared and c is equals to 0. We now derive a sufficient condition. Okay, so the theorem 13.8. For some integers n is greater than or equal to 1, let f have the continuous nth derivative in the open interval of a and b. Suppose also that for some interior points c and a and b, we have f to the power of 1 of c is equals to f to the power of n. Is it 2? I'm not really sure. So it's okay, so just read that. Okay, so then for n, even if has a local minimum at cf, f to the power of n of c is greater than 0, and a local maximum at C if f to the power of n of c is less than 0. If n is an odd, there is neither a local maximum nor a local minimum at c. Okay, so this is the proof. Since f to the power of n of c is not equals to 0, there exists an interval b of c such that for every in b of c, the derivative of n to the power of n of x will have the same sign as f to the power of n of c. Now, by Taylor's formula in Theorem 5.19, for every x in b of c, we have this one. Okay, so this is the Taylor's formula. Okay, just to read it because I am not really sure on how to read this one. Okay, so please next. If n is even, this equation implies f of x is greater than or equals to f of c when f to the power of n of c is greater than 0, and f of x is less than or equal to f of c when f to the power of n of c is less than or equals to 0. If n is odd and f to the power of n of c is greater than 0, then f of x is greater than f of c when x is greater than c, but f of x is less than f of c when x is less than c, and there can be no extremum at c. A similar statement holds if n is an odd and f to the power of n of c is less than 0. So this proves the theorem. Okay, now let's move on to the next page. Okay, let's move on to 13.6. Extrema of a real valued functions of several variables. We turn now to functions of several variables. So in exercise 12.1 gives a necessary conditions for a function to have a local maximum or a local minimum at an interior point A of an open set. The condition is that each partial derivative d sub k f of a must be 0 at that point. We can also state that in terms of directional derivatives by saying that f a and u must be 0 for every direction u. So the converse of this moment statement is not true. However, consider the following examples of a function of two real variables. Okay, so this one, f of x and y is equals to the quantity of y is equals to minus x squared and y minus 2x squared. Okay, here we have d sub 1 f of 0 and 0 is equals to d sub 2 of f of 0 and 0 is equals to 0. So now f of 0 and 0 is equals to 0. But the function assumes both positive and negative values in every neighborhood of 0 and 0. So there is neither a local maximum nor a local minimum at 0 and 0. Okay. So see figure 13.3 for this. This example illustrates another interesting phenomenon. If we take a fixed straight line through the origin and restrict the point of x and y to move along this line toward 0 and 0, then the point will finally enter the region above the parabola. Y is equals to 2x squared, or below the parabola is y is equals to x squared, in which f of x and y becomes and stays positive for every x and y is not equal to 0 and 0. Therefore, along every such line, f has a minimum at 0 and 0, but the origin is not a local minimum in any two-dimensional neighborhood of 0 and 0. Okay, please next. Let's proceed to the next page. Okay, so let's the 13.9, the extrema of function of several variables. Okay, just look at the graph here. So that is the example. Okay, so this is the 13 figure 13.3. Okay, in 30 and definition 13.9, if f is differentiable at e and f, I don't know how to read this symbol. The point A is called the stationary point of F. A stationary point is called a saddle point of every n ball. B of A contains point X such that F of X is greater than F of A and other points such that F of X is less than F of A. Okay. In the foregoing example, the origin is the saddest point of a function. To determine whether a function of n variables has a local maximum, a local minimum, or a saddle point at a stationary point A, we must determine the algebraic sign of x of f minus f of A for all x is a neighborhood of A. As in the one-dimensional case, this is done with the help of Taylor's formula. So remember the Taylor's formula in 12.14. Okay, take m is equals to 2 and y is equals to a plus t in theorem 12.14. Okay, so the partial derivatives of f are differentiable on an n ball of b of a, then f of a plus t minus f of a is equals to, I'm not really sure on how to read this, times t plus, how to read it, I don't know how to read the symbols also. So just to read it. Okay, so next slide, please. Where z lies on the line segment joining a and a plus t and f to the power of n of z and t is equals to the summation of n and I is equals to 1 and the summation of g equals to 1. So d sub I and j, f of z, t sub I and t sub j. Okay, at a stationary point we have this symbol of f of a is equals to 0. So 3 becomes f of a plus t minus f of a is equals to this one. Okay, just to read it. So therefore, as to a plus t ranges over b of a, the algebraic signs of a plus of f of a plus t minus f of a is determined by that of z to the I'm not really sure on this. So we can write 3 in the platform. Okay, so this one. Just look at this. Okay. So shows that e of t to 0 as t to 0 if the second order partial derivatives of f are continuous at a, since this one I'm not really sure how to read this, tends to 0 faster than t squared. It seems reasonable to expect that the algebraic signs of f of a plus t minus f of a should be determined by that of this one, f with a 2 power of a and t. This is what is proved in the next theorem. Okay, so next page. Okay, so this is the theorem 13.10, the second derivative test for extrema. So assumes that second order partial derivatives d sub I g f exist in an n ball of b of a and are continuous at a where a is a stationary point of f. So let this one, so just read it. And we have also a b c here. Okay, so the you read it the from a b and c. Okay. So now prove the function q is continuous at each point t in R to the power of n. So let S is equals to this one. Just read that one because I don't really know how to read the symbol. Denote the boundary of the n ball of B of 0 and 1 if Q of t greater than 0 for all t is not equal to 0. Then Q, I'm not really sure if it is read as Q of t is positive on S. Since S is compact, Q has a minimum on S. Call it M, and M is greater than 0. Now, Q of CT is equals to C squared Q of T for every real C. So taking C is equals to this one, just to read the symbol. Okay, so you just read all of this one because I'm not really sure on how to read all this symbol. Okay, so therefore F has a relative minimum at A, which proves A. To prove B, we use a similar argument or simply apply part A to negative or minus F. So finally, we prove C for each this one I forget and how to read the symbol greater than 0. So we have from 4. Okay, so that's all my report and I am Geneva Cataño, your second reporter for chapter 13. Okay, so thank you.